Hi guys, sorry we had some technical difficulties, but we finally got everything to work. So today we have Sinan talking to us about primes, means and logs. Enjoy.
Hello and welcome to my talk. I am Sinan Deveci, currently studying mathematics in first semester here, and I'll tell you today about my matura thesis where I did some research in number theory. Let's start with primes. How many primes are there? Well, obviously infinitely many, but it would be nice to know how many there are in a given range. For example, less than a given integer. In the 1900s, mathematicians have posed themselves this question and defined a function called pi of x. Yeah, it's quite unfortunate. It has nothing to do with the constant pi, which is 3.14 and so on. I guess it's just because prime starts with p, and then the Greek p is the pi. And so pi of x is defined as the number of primes less than or equal to some integer x. For example, pi of 5 would be 3, because 2, 3, 5, there's 3 primes less than or equal to 5. Yeah, now we have defined this function, but can we, now as primes are quite a difficult beast, there's probably no simple way to describe pi of x, but we can approximate it. And in the 19th century, several mathematicians have found this approximation, that asymptotically pi of x is equivalent to x over log x. Log, as in the whole presentation, will be the natural logarithm. And this is quite remarkable because prime numbers have some connections to logarithms, and x over log x does not seem too complicated. If someone were to ask you how many prime numbers are there less than or equal to x, you would probably think it would be a really complicated expression, but now we have just x over log x, which is pretty good. Obviously, the approximation gets better and better the bigger the input gets. Now, a small digression to the Euler-Mascheroni Constant. Some call it the Euler-Mascheroni Constant. Now, this is denoted by gamma, and really important in number theory. It appears all the time. And you see, it's just the... by the way, can you see it, or am I in the way? So it's just the difference between the harmonic series truncated at some number n and the natural logarithm. Log obviously is not in the sum because it's not dependent on k. And now the sum we can just write as hn, the harmonic number n, because it's the harmonic series just cut off after n summons. And that's about 0.577. So the harmonic series is really close to the logarithm. And perhaps you remember that if we were to take the integral instead of a sum, then we will get exactly the natural logarithm. So it's perhaps not all too surprising. Yes, so this is 0.577 approximately. Now let's go back here. But now we can say, because the difference between hn and log n is asymptotically finite, just 0.577, let's see if we can just, so they are about the same. Now, well, we have this and this, so let's just replace log x with hx, because the error should not be too large. And yeah, now we have reformulated the prime number theorem to this. Now at first glance it seems like we haven't made much progress. Now we have just one symbol instead of 3, so maybe that's a bit better. Now, another digression, I'm afraid, to the harmonic mean. Yeah, there are many different types of means. The harmonic mean is one of them. So you take you have a collection of values and you want to find some sort of average. The harmonic mean is one way of doing that. Depending on the data set, some mean is better than some other mean. But we'll learn that in statistics. And yeah, so you take all the terms and add their reciprocals, take the reciprocal of that and multiply by the number of entries. For example, harmonic mean of A, B, and C, it's just you flip everybody, add them, and then 3 over that because we have 3 terms. The harmonic mean of 1 over 4 and 1 over 6 would be 2 over 1 over 4, which is 4, and the same with 6, which is 1 over 5. And that's where the name harmonic series comes from, because the individual terms are in harmonic progression. And then obviously there's the connection to music. So the harmonic mean of a quarter and 1 over 6 is 1 over 5. So 1 over 4, 1 over 5, 1 over 6, and so on are said to be in harmonic progression. Now, what I did is I defined a function denoted hm of x, which just takes the harmonic mean of every positive integer 1 up to x, because it's a bit cumbersome to always write the dots. Yeah, and so then when we plug in this into the definition, we just get this and then this. And now in the bottom, we again have the harmonic series truncated, so it's 1 plus a half plus a third and so on, which can be abbreviated as hx, the harmonic number x. Now, if we come back here, as we have seen, x over hx is the same as the now newly defined hm of x. So we can write this. And now that's pretty amazing, because hm of x is just some mean between all the natural numbers from 1 to x, and somehow this is asymptotically equivalent to the number of primes up to that magnitude. And so primes, of course, are really special, but now we have seen that somehow if you want to take the average or element of 1, 2, 3, and so on, then it's really close to the number of primes up to there. And I have no idea why this is like that, but yeah, pretty cool. And now as a corollary, because this is just the mean, and then if you take more and more numbers, such that the maximum element gets larger and larger, then obviously the mean also gets larger, and so pi of x gets larger, and so there are infinitely many primes. So we have now one more proof for that, which, but it's kind of useless because there's already so many proofs, but it's nice that we can demonstrate a fact that we know to be true. Okay, and now there's always this asymptotically equivalent sign, which is perhaps a bit bothering because, it's approximately the same and gets better and better for the larger and larger x gets, but how exactly is the error? In the 1850s, the Russian mathematician Chebyshev posed himself this question for the original prime number theorem, and he came up with the bounds of 1 over 6 to 6, right? Because h over hx, or h over log x, that should be x over log x, is about pi of x. So if they are exactly the same, the fraction should be 1, but they're not exactly the same, so it's between 1 over 6 and 6. Now, when we plug in, it should be log x instead of hx. When we plug in hx, then the lower bound stays, the upper bound gets a bit worse. We failed. But we now can compute it only with elementary operations, right? Because hx is just the harmonic mean, so we add the reciprocals, and then we divide the number of terms by that. So we only use plus, minus, multiplication, and division to estimate pi of x. Before, we actually use logarithms, for which computers or big tables are necessary. So now we can approximate the number of primes up to a given integer using only elementary operations. Now we have discussed the primes part pretty much, and we have used harmonic numbers and harmonic means. So let's investigate means in general. Now, the classical means from ancient Greece are the Pythagorean means. The arithmetic mean, is the classical mean, so it's just you add all the entry elements and then divide by the number, so that's like the normal average. But you can also multiply them and then take the nth root. For example, the geometric mean of 2 and 5 would be the root of 10, which is about 3.16, which is less than the arithmetic mean 3.5, but which may be, depending on the data set, better to use. Because, maybe if you look at the earnings in a the salaries in a company, and then there's one guy who earns really much, and then the rest not that much, and then the arithmetic mean would be quite skewed to the high earning side, but the geometric mean a bit less. So really depends on the data set. Obviously, if one of the xi is 0, then everything is 0, and that's not that good. And the harmonic mean we already know. Now, German mathematician Otto Hölder generalized these means and more to this formula. So now, the big M just stands for mean. The little m is like the index, which mean we take. If it's 1, it's the arithmetic mean. If it's -1, the harmonic mean. If it's 2, the quadratic mean, and so on. And then, just of many values, and that's this. For example, if the small m is 1, then we just get xi to the 1 is just xi. We add them all up. We divide them by n, the number of entries. And then the first root is just the identity. So we have exactly this, which we already know. Now, but that only works if m is non-zero, because otherwise we would have to take the 0th root. Well, root is just 1 over something in the exponent. 1 over 0 is bad. Then the geometric mean, we have to take the limit as m goes to 0, and then we use some logarithms and exponential, and then this becomes a product. And then it works, but we're not going to do that now. Basically, then we get, then the sum magically becomes this product here, and then it works. Now, again, my idea was, it's a bit long to always write the 3 dots. So, and I'm really only interested in natural numbers because they are the ones, the oldest ones, and they probably come closest to existing. So let's define this function, which just takes the m mean of all natural numbers up to x. So, and I switched the index from I to k, because it might get confusing later otherwise. And so we just have this guy. Now, so we have this function. Now, what could we ask ourselves about this function? Well, maybe just play with the x, make it really big. So asymptotic behavior, and then we get this. So for the arithmetic mean, we just get 1 over x times the sum over the I, which, as the little Gauss already knew, is x times x plus 1 over 2. And then we get this. And yeah, this makes sense because the normal average of successive positive integers should be around half of the biggest integer. Then for the geometric mean, yeah, we multiply all of them and we take the square root. Now if you multiply 1 times 2 times 3 and so on, that's factorial. So we get this, and this we already did. But that's in general. Now we want to see what happens if the x gets really large. Then obviously arithmetic mean stays. Then the geometric mean, the first term is x over e, and then we get some smaller terms which we ignore. And yeah, hx, as shown in the beginning, is log x plus gamma. So we get this. So already we see a pattern emerging, because it's just, we have some fractions, and yeah, it's just x divided by some constant for the first two. Here it's a bit different. Now let's keep going and just change the index, the little m. Now we take the quadratic mean. So the k has exponent 2, and then we take the normal square root. Now, if we sum squares, I think that's called the pyramidal square identity or something. Then we get x times x plus 1 times 2x plus 1. For those who are also in first semester, I think this was in an analysis exercise. And then we get this. And then asymptotically, we get x over root of 3 plus root of 3 over 4. And then the same thing for m3 and m4. Yeah, you can easily check this just by plugging it into your Wolfram alpha, which is also what I did. I didn't do all of this by hand, obviously. And then in general, we can extend it to this. So we have x over some constant, which comes from a root, and then plus some other constant, basically, for all m greater than or equal to 2. So for arithmetic mean, so for quadratic mean, cubic mean, and so on. Now we do the same thing for where the little m is less than or equal to negative 2. And yeah, you can use generalized harmonic numbers for which the domain is extended. But yeah, let's look into the details. Basically, we just find this identity, and now we see there are roots. So it's the negative mth root of x. So before, we have just x and times some constant, but here we have some root of x. And here also in this identity, the case where m is equal to 1 and 0, they're also included. And so we get this. If the small m is greater than negative 1, we get the first pattern. So x times some constant plus another constant. If x is less than negative 1, we get the other pattern. And if x is negative 1, we get a third thing. So we get two different patterns, one on the right side of negative 1 and one on the left side. And yeah, that's quite remarkable because we just took basically all the means of this function of really big integers, and then we get two different patterns. So we have here a pattern and here a pattern, and now I guess the natural question would be what happens here when you transition at the phase transition, basically between one pattern to the other pattern. And now the problem is to go there. Well, if you just plug in negative 1, you get what's written on the bottom. But that's somewhat unsatisfying because now we also get logarithms which do not fit in any of the patterns above. So let's approximate it. But if we come from the right side, then we're always trapped in the pattern above. If we come from the left side, we're trapped in the pattern in the middle. So what can we do? Well, just come from both sides at once. And this is done using a trick called the Cauchy principal value. It's also used to give some value to the diverging series theta of 1, for those interested. Basically, you come from the right side, and from the left side, you add them up and you divide by 2. So you just take the arithmetic mean this time. Obviously, it will also be interesting to see what happens if you take the geometric mean or the harmonic mean, but that would be too many steps. So now, if epsilon is 0, then this collapses and we just get m-1 of x. But if it's not 0, then we can define this function. And now what we... basically, so if epsilon is 0, we just get m-1 of x, which is the harmonic mean function. Now we want to investigate the transition at -1. So we need a sequence for epsilon that is going to 0. Let's just take 1 over n. That's the first thing that came to my mind, so let's use that. And then we get, if we calculate this, we get this another sequence. So basically I just put it into Wolfram alpha and took the first term because it's really long. And then the first terms are, so it's x over 8 plus over something. And then if epsilon is 1/2, if epsilon is 1/3, we get this, and so on. And so we just invented a bunch of functions, and now we got a sequence. Right, here it's the second root, third root, fourth root. So it's pretty consistent. The only thing that's non-trivial is the radicand, 8, 108, 2048, and 50,000. So we found a sequence. What do we do when we find a sequence? Well, we look it up, if it already exists. And yes, it did. In the OEIS, it's the Online Encyclopedia of Integer Sequences. There, almost all sequences are listed. And then if you found something, you can check whether someone else found it, and then you find some unexpected connections, which I did, or so I thought. Because as it turns out, this sequence is already listed as an entry for the discriminants of the Chebyshev C polynomials. And those are important in approximation theory, it said. Well, I don't know anything about approximation theory, but cool. My physics teacher told me that these polynomials are somehow important in the decay of nuclei. So then I thought, wow, I just played with some stuff in pure math, which should have no applications, but then suddenly I'm doing nuclear physics. How exciting. But then I checked the page again, and it turns out it's probably just a coincidence, because there's a simple formula like this, and to create the sequence. So it's really simple. It's just 2 times n to the n over n minus 1, so probably no nuclear physics this time. So we investigated the case where x gets really large, so asymptotic behavior, and found some more, some less interesting things. What would be a natural question now? Well, we went really big. Now let's just go the other way, really small. X going to 0. But wait, that's illegal. Because we defined our function to take some mean of all positive integers bigger than 1 and less than 0. And there is no integer bigger than 1 and less than 0. It's the wrong way. But if we look back for the identities for arithmetic, geometric, harmonic mean, and so on, when we calculated the asymptotic behavior, we found an alternative representation, and here you can just plug in 0. Here you can plug in 0. Here you can, okay, here you can't, but so, you can take the limit, and then you can somehow plug in 0. So it's again we're using a trick, which is extend the definition, the domain of the original function. It's a bit like the zeta function. So the zeta function is some sum, and this sum diverges for certain values, but then you can somehow extend it, and then it works. That's where the -1/12 comes from, if you're familiar with that. So we did some illegal thing, and we got 1/2, e to the negative gamma, and zeta of 2. So really interesting constants, which are, which come up all the time in math. Now, again, keep going. AM, GM, and HM are little m index 1, 0, -1. So now let's also do 2. Here again, we know the analysis exercise, x times x plus 1 times 2x plus 1 over 6. And here the x's cancel. Then we can plug in 0 for x, and we get this. And so now we see that for odd m, like for example 3, we get 0, and other times we get some root. And if little m is congruent to 2 modulo 4, we get a real number. If it's divisible by 4, we get an imaginary number. So, but that's exactly this. The Bernoulli numbers, and then just the mth root. Bernoulli numbers are also really important numbers, which appear in number theory a lot. But basically the only important thing for this talk is that Bernoulli numbers are cool, and now we found some other appearance of them. And then they can also be represented as -m times zeta of -m plus 1, which we keep in mind for later. So now let's do little m is negative. And then, just compute, and we get this. So again, some pattern, quite regular. And so again, x going to 0, we cannot put 0 there, but we do it anyway, and then we get this pattern. And then in general, we get this thing here. So basically that's just this, right? The 1, the zeta, and so on. For m less than or equal to -2. And so this thing is exactly the same thing we found before for the positive index case. So we can generalize, we can combine the two to this. And so m of 0 doesn't exist, but we pretend it does anyways. And then it's equal to this for all tiny m not equal to 0. If it is 0, then again we take the 0th root, and also zeta of 1 minus 0. So we do a bit too many illegal things at once. But they cancel out. Well, now obviously it doesn't work, but we can just take the limit. So basically we have our function, and then at 0 we have a hole in it. So how do we fix it? We just take the limit. And basically what I did is I just opened Wolfram alpha and typed in limit blah blah blah, enter, and it said e to the negative gamma. But proof by Wolfram alpha doesn't exist, so I had to do it myself. And then I don't know how it happened, but somehow I guess I was bored, or I was stuck and then procrastinated and did something else and just read some Wikipedia. Also, and stumbled across the entry for Riemann's functional equation for the theta function. which is this. And we can use it to prove the identity above. So just by mere luck, I opened this page with this really complicated thing, and then I thought, oh, I can use it for this one, and then I proved it. So that's a functional equation. So it's like some normal equation where you have to find a variable, but now you have to find a function. So yeah, it's like a differential equation basically, but just not derivatives, but the function at s and at 1 minus s are related by this thing. Now the proof, it's a bit long, so I'll just quickly say a few things. So first I proved that this thing is 1, and I did that by proving these two things. And then, the lemma you can prove by L'Hopital, and then set s equal to 1 minus m, and the rest is left as an exercise. If you don't want to do the exercise, you can also read the entire paper. The link will be there in the end. But now, lastly, let's also watch some log thing. So, the theme of the talk is, when we look back, is harmony. I didn't really intend it. I just had several things that interested me, and then for the criteria, one criterion was that it should be somewhat coherent, and so then I had to look back and invent something that ties them all together, and that's luckily harmony, right? Harmonic series, harmonic means, harmonic numbers. So now, alternating harmonic series. So the harmonic series diverges, of course, but if we alternate it, we go up and down, and then oscillate, and then it converges to log 2. This has been known for centuries. But if you stare at this for as long as I did, you start to wonder, what's so special about 2? Right? Because here, it's just the harmonic series, you manipulate the signs, and then you get log 2. But you did nothing really special here. So you should also be able to manipulate the harmonic series in some ways to produce log 3, log 4, and so on. But I didn't find anything. Somehow, only log 2 is important. I don't know why. So then I asked myself, how can we somehow extract the 2 from here and put in a 3 to get log 3? Well, the first thing is, it's plus minus and so on. So we always alternate. So maybe invent a third sign. Right? So we have like plus, minus, and then the new sign and so on. But there's only 2 signs. And if we do it with complex roots of unity, then that also doesn't work. But you can say that we add the terms with odd denominators and subtract the terms with even denominators. A bit more precise, well, not precise, but more practical and hinting at the thing we want to do. We subtract the terms where the denominator is divisible by 2 and add the rest. Right, this can be written as this. And then, again this. And so now, let's just subtract the terms where the denominator is divisible by 3 and add the rest. Oh, nope. It diverges. Because we add, subtract. We always grow, right? We add more than we subtract. So how do we fix this? We have to subtract as much as we add. But if we somehow change it, then it also doesn't work. But let's just change the weight. We have to subtract twice. So let's write 2 instead of a 1 in the numerator. So I did that, put it into Wolfram alpha, and boom, log 3. Wow. So we just subtract twice because we add twice, and then we get this. And then, of course, generalize. For log 4, exactly the same thing. Add everybody. Subtract the multiples of 4 in the denominator, but 3 times because here is 3. And then generalize the whole thing to this. Now you get a nice double series. Yeah. And so here, yeah, you add the terms which are a multiple of m but offset by k, and subtract the multiples of m in the denominator. And that's this. Actually, it's for all integers m greater than or equal to 1, because if you put in 1 for m, then you sum for k from 1 to 0, which doesn't exist, so it's just 0, 0, 0. And then log of 1 is also 0. So, yeah, just by wondering about this, right? What's so special about 2? Why is there 2? We found this thing. And yeah, now these are all modifications of the harmonic series that give some logarithm. And now that's a bit abstract, but basically if you want to compute log 4, you just compare every unit fraction to the unit fraction whose denominator is divisible by 4 that is closest to it. For example, log 4 is 1 minus a quarter plus a half minus a quarter plus a third minus a quarter plus a quarter minus a quarter, right, at 0, plus a fifth minus 1 over 8 plus 1 over 6 minus 1 over 8, and so on. So just you have, I imagine it like this, you have some sequence and another sequence, and here are 1, 1 half, 1 third, 1 over 4, and so on, 1 over 4, 1 over 8, 1 over 12, and so on, and you just compare, pairwise this minus this, and then you get log 4. So the logarithm is actually really easy, because you just always take the difference. Now, the whole paper with some more rigorous proofs and less hand-wavy, you can find here. Feel free to check it out. And otherwise, thank you for your attention. Any questions? Yeah?
Could you go back one slide to the link?
Yeah, of course. Oh.
I'll put the link on the website as well. So
Oh, perfect.
take photo.
Yeah?
What motivated you?
Oi. So I was always interested in math, and also did it in my free time in gymnasium. Yeah, and then we had to write this Matura thesis, so I thought, why not combine it? And yeah, basically, yeah, it's like play, I guess, because you have something like the alternating harmonic series, and then you look at it, you poke it a bit, see how it reacts. You look at the individual parts to see what they do. What happens if I take this away? What happens if I add this? And then you get some new things. So, yeah, it just curiosity, I suppose. And like for other people, it manifested itself by disassembling laptops and seeing what's inside. And for me, it's just a more abstract series and stuff. Yeah. Yeah.
One thing, if I didn't misunderstand, at some point there was a slide where x divided by the harmonic series up to x goes to 6 divided by pi squared as x goes to 0. Could you explain how that?
Oh, yeah, of course.
Really
Sorry.
weird.
Oh, here, yeah.
Exactly. The harmonic series. How does the harmonic series make sense for values less than 1, like for non-integer values?
So basically, you can generalize the harmonic series or the harmonic numbers hx are related to the digamma function, which is the derivative of the logarithm of the gamma function, which pops up all the time. And then it's like you extend the factorial to real numbers with the gamma function. You can extend the harmonic series, the harmonic numbers, to non-positive integers with the digamma function. And then you get something. It's still 0, so you get 0 over 0. But then you do some limit trick, and then you get this. And by the way, 6 over pi squared is also the probability that if you choose 2 random positive integers, that they are coprime. And also, if you drop some Mikado sticks, then this number also pops up. So it's really everywhere.
So the limit goes to infinity of the probability.
Yeah, in the limit, of course, as all things should be. Yeah, so if that's everything, then again, thank you.